This video is still talking about exponential functions, but now we're specifically talking about the natural exponential function. And it's the natural exponential function because we have this natural base e. And here you can see e is approximately equal to the number 2.718. E is representing a constant number. And this looks very similar to a number we've talked about before, and you're probably familiar with the Greek letter pi, and we know that pi is approximately equal to 3.14. So just as pi is representing a constant number, such as 3.14, and we know that this decimal continues. The same thing is true for this natural base e. It's simply representing this decimal, which is approximately 2.718. So when we look at the function, we have f of x equals e to the x. And I know you probably get a little confused thinking, wait a second, there's no numbers in this function. But really, this function would be very similar to saying f of x equals 2.718 raised to the power of x. But instead of using this 2.718 as the approximation, we want to use this letter e because that's going to give us a more accurate answer. So for example, if we go to the calculator, on your calculator, you'll notice that over here where you have your division key, right above it you see the letter e. So if I hit second function and e, and if I was to hit enter, we're going to get the approximation for E, 2.718281828. And again, this continues on forever. There's also another number over here. If you notice over here next to the number 7 key, there's a log button. And then below here, below that, you see ln, which you see this e to the x. So if I hit second function and this e to the x button, this is the same e, so for example, if I raised it to the exponent of 1, I'm going to get the exact same number. But if I was to take second and then e to the x and then plug a 2 in, then it's going to square the number and I'm going to get 7.389. Now, for example, if I was to take the number e, which we said e is approximately 2.718, so if I take 2.718, now, if I round that and just leave it as 2.718 and raise that to the second power, notice I get a number that is somewhat close here, 7.389, and here we get 7.387. So it's accurate out to 2 decimal places, but notice how the number changes. That's why we want to use this letter E, because it's going to give us a better representation of this number. So when we talk about this natural base E here, it's representing this approximate decimal here, 2.718. So it's a little bit less than 3. So really nothing else has changed except for this is representing our base. Okay, now if we look at the graph of this function, and let's see, we can actually go to the calculator and do that. If we go to y equals, we could type second e. Now remember, we want to raise this to the x power, so that's e to the x. And if I go to zoom standard, notice here our graph certainly does look like our e to the 2x, or I'm sorry, f of x equals 2 to the x, because remember, this is 2.7 approximately. So if we were to go in here, for example, I'm going to go down here and type in the function we looked at in the previous video where we had 2 raised to the power of x. Now these graphs should be very similar because e, remember, is really 2.7, so there's not going to be a whole lot of difference between the graphs. And let's see, I'm going to go in front of, move the cursor here in front of our y2, and I'm going to hit enter a couple of times, maybe 3, 4 times here, I guess, until we get this little flashing line with an open circle. So now when I graph, this is going to trace out with this open circle. So if you notice when I hit graph, here comes the graph of our other function here, 2 to the x. And if you notice, it's very close to this graph, and really there's little difference here. Notice here it's not increasing as fast because if we have 2.7, it's obviously going to increase at a much faster rate. And you could probably guess what would happen instead of 2 to the x, what if I go down here and graph 3 raised to the x power? Well, if we hit the graph here, it's going to go on the inside here a little bit closer. Notice it's to the left of e to the x because it's going to increase a little bit faster than the 2 to the x. So if you notice here, they're almost identical because one is 2.7 to the x and one is 3 to the x. So there's very little difference here between the two different graphs. So here, when we graph e to the x, we're still going to end up with the similar properties that we had before, where our graph is still going to be increasing, and we're still going to have this y-intercept that occurs at 0, 1, unless we start moving the graph left or right or up or down. So just your basic function here, e to the x, again, it's going to be increasing. Now, of course, if we put a negative in front, then it would be decreasing because that would be a reflection in the y-axis. Okay, so for example, let's go down and look at a couple examples of our function. If we had e raised to the x minus 2, what effect is that going to have on the graph of our function? Well, this is on the inside of the function, so that means we would take x minus 2, set that equal to 0, so that means x equals a positive 2. So therefore, our graph is going to move 2 units to the right. So where the e to the x normally is here, it's now going to move 2 units to the right. So that means this y-intercept is going to move to here. So then your graph's going to look something like this. And then, of course, if we go to the next example, we still have the e to the x plus 2, but now we have a plus 4. So once again, if we look at the basic graph e to the x here, this is just e to the x. We still have this y-intercept at 0, 1. But now the x plus 2, here we have an x plus 2. So what effect is that going to have? That's going to move our graph 2 units, because if we take x plus 2, set that equal to 0, we're going to get a negative 2. So that's going to move us 2 units to the left. So this point now is going to move here. Okay, so that means our graph at this point would look something like this. But then we have the plus 4, that's going to move the graph up 4. Now keep in mind, this here is at 1. So if we move up 4 units, 1, 2, 3, 4, we're now going to be at 2, 3, 4, 5. This is going to be at 5. And then our graph would go like this. So here we would have the function e to the x plus 2 and then plus 4, which is going to move it up 4 units. Now keep in mind, the horizontal asymptote that we had here at the x-axis, that's also going to move up this same 4 units. So if it moves up 4 units, well, if it starts here at y equals 0, it's now going to be up here. The horizontal asymptote would now be y equals 4. So everything's going to be moved up 4 units. Okay, and if we go to the calculator, we could look at this. If we were to graph e to the x plus 2, so let's clear out the other graphs here. If we go up and we graph e to the, now it depends on the calculator here, you may need to actually put parentheses for the x plus 2 because you want to make sure the calculator knows that you're raising the entire x plus 2 as your exponent, and then close the parentheses, and then we have the plus 4 on the outside of the parentheses. So if we again go to zoom standard, we can see that our graph here has moved over to the left, and also it's moved up 1, 2, 3, 4. Here is your at 4. So let me actually graph that. If I went in here, we said the horizontal asymptote was at 4. So if I graph y equals 4, here's the horizontal asymptote, and notice our graph's never going to cross that, and then it continues to go up. So our graph here has moved 2 units to the left and then up 4 units. So here, even though we're talking about this natural base e, The only thing that is this e is representing the decimal 2.78, and then everything else is going to hold true that we talked about with our exponential functions in the previous video.